Okay, let's do another kinematics problem. So I grabbed this one from the MIT OpenCourseWare website, and I'm just going to show you how to get there so that you can find example problems to work on your own. So this is the website, MIT OpenCourseWare, Massachusetts Institute of Technology, and I went to their course finder, and I just put in engineering, mechanical engineering, dynamics and control, and I went to fall 2004, view course, and this website, they MIT records all of their lectures, and they provide like assignments and old exams and stuff like that to the public. I guess for the greater good, and so we're gonna use it. So I went to assignments on this left tab, problem set 2, and it's somewhere here. There it is. So this is where I got the problem from. Let's read the problem. The disk rotates at omega 1 about its axis, and the rotation rate of the fork shaft is omega 2. Okay, so the fork is rotating at a rate of omega 2, and the disk is rotating at a rate of omega 1. Both rates are constant, so that tells us that omega 1 dot and omega 2 dot are 0. Determine the velocity and acceleration of an arbitrarily selected point B on the perimeter. So we have some point on the perimeter of the disk, and we want to find the velocity and acceleration. Describe the results in terms of components relative to the x, y, z axes in the sketch. All right, so there's another piece of information I think you need, and they didn't explicitly say it, but we're going to call the radius of the disk r. Let's set up our reference frames. So they already set up our first one, really, with this x, y, and z. I'm just going to rewrite that right here. This is going to be our inertially fixed frame, fixed to ground, fixed in G. And we're going to call it, cap EX, cap EY, capital EZ. Our next frame is going to be this frame F for fork, which is what they called this. And this rotates with the fork. And EX points along this shaft, and it always points along this shaft. EZ points straight up. It's in the same direction as the red EZ. Our green EZ and our red EZ are going to point in the same direction for all time. And then EY is going to be equal to EZ crossed with EX. So if the fork were to rotate out here a little bit, then EX, the frame F would rotate with it. So EX would be pointing in this direction now, EZ still straight up, EY would be EZ crossed with EX. All right, so that's the frame of the fork. And then lastly, we have this frame fixed to the disk. So fixed in D. In this yellow frame, UR is pointing from the center of the disk, point A, out to our point of interest, point B. So that's UR direction. UZ is perpendicular to the disk. It's perpendicular to the disk, and it's going backwards in that direction. That's UZ. And then U theta is equal to UZ crossed with UR will give us U theta. And you can see it's perpendicular to our plane of rotation here. All right, so that's our setup. I'm going to let theta dot equal omega 1, right? Because that's what it is. The rate of change of this angle is the rate at which this disk is rotating. So it's theta dot is omega 1. And then I'm going to call this dummy variable rho 2 dot. And that's going to be equal to omega 2. So what theta is to omega 1 is what rho 2 is to omega 2, right? It's just the angle that the fork is rotating at. So the rate of change of that angle is omega 2. And this is just used for our DCMs, which I'm going to start right now. We're not going to use all of these DCMs, but we're going to do it for practice because we're learning. All right, so let's go from the red basis to the green basis. I have a whole video going over direction cosine matrices, and I have an example going through the rotations. So I'm going to assume you've watched those and are a little familiar with it because I'm going to go a little quicker in this one because I assume that we hopefully learned something from the last video. So to go from the red basis to the green basis, all we do is a -3 rotation, by rho 2, right? It's the angle that this fork makes. That's how much we rotate this to get to the new green basis. So this is our fundamental 3 rotation matrix, and I just plugged in negative rho 2. And then cosine of a negative angle is just cosine of the angle. And then sine of a negative angle is negative sine of that angle. And then we did the same thing for these last 2 terms. Okay, so this is our basis from red to green. This is where you were, this is where you were going. And this is our DCM to get us there. Next, let's do going from the green basis to our yellow basis. So let's talk this through real quick. And the way we're going to do this is we want to align, the 1 axis with the 1 axis, the 2 with the 2, and the 3 with the 3, right? So we want EX to line up with UR, we want EY to line up with U theta, and we want EZ to line up with UZ. So the way we're going to do that is in 2 rotations. First, we're going to do a negative 2 rotation by 90 degrees. And when we do that, that's going to make EZ point straight back. That's going to make EX point up. This is EZ now. And then EY stays the same. So now we only need to do 1 more rotation to line this up with the yellow basis. And we're going to rotate by an angle of theta, about the new 3 direction, this new EZ direction. And that will swing EX down and point in the correct direction. So now we would have EX pointing in this direction, EY pointing in this direction, and EZ pointing in that direction. So now we're lined up, right? So we did a 2 rotation by negative 90, and then we did a 3 rotation about our new 3 axis by theta, and that lined us up. Again, go watch the video on DCMs if you didn't follow that. So this is our fundamental 2 rotation matrix by negative 90, and then this is our fundamental 3 rotation matrix by theta. I'm not going to go through the multiplication. I believe you can do it. And what we would end up with is this right here. So this would be our DCM that takes us, gives our relationship between the green and the yellow basis. Finally, we're not going to use this one, but we're going to do it for practice. Going from the red to the yellow basis. What is the DCM for that? Well, we just have to plug in for this green one, and we already know the green one, right? The green basis is equal to this DCM times the red basis. So we're just going to plug in this for the green. So we did that. Here's the green, here's what we plugged in, and then we do the multiplication. Voila. Now we have our red in terms of, or yellow in terms of the red basis here. This is our relationship between the 2. All right, so DCMs are done. Fantastic. That's the hardest part of this whole problem. And now we're going to get to the kinematics. So we always do these problems the same way. We first write our position vector from an inertially fixed point out to our point of interest. What inertially fixed point are we going to pick? You can pick any inertially fixed point you want. I'm going to pick point A because I think that's the easiest. And why is A an inertially fixed point? It's because it lies on the axis of rotation of both the fork and the disc, right? So since point A is right here, no matter how those frames rotate, F, the fork and the disc, A is going to stay in its same spot. It's not going to move. It's going to remain inertially fixed. So that makes our life easy because the position vector from our inertially fixed point A to point B is just R, where R was the radius of the disk, is just R in the UR direction. There we go. We got our position vector. Right here, RUR. If we want to find the velocity of that point, then we take the derivative of the position vector, which is exactly what we're doing, just plugging right in, RUR. We can take out the constant R because it's a constant. The radius of the disk isn't changing with respect to time. And so now we just have to find this DUR dt. To do that, as you'll recall from our previous video, and I have it written down here, this is the rate of change of a unit vector in a rotating frame. And the way you do that is you take the absolute angular velocity of the frame you're interested in and cross it with the vector itself. So we need this omega, the angular velocity of frame D and G. And from our addition theorem of angular velocities video, we know that the angular velocity of d in g is equal to the angular velocity of d in f plus the angular velocity of f in g. Remember that backstepping thing we did in that video, right? We can go from d to f, and then from f to g, and if we add those up, then we'd have d in g. So that's exactly what we're going to do. So let's find these terms. F in g, what is that? Well, that's negative omega 2 ez, right? Because f is rotating like this with respect to g, and that is a negative, that's a negative ez rotation. So negative omega 2 ez. And then while we're here, how is frame D rotating with respect to F? Well, you could write it one of two ways. It's either doing a positive 3 rotation about UZ, so it's either omega 1 UZ, or, the disk is still rotating in this direction, or this is a negative 1 rotation, so negative EX, a negative 1 rotation. So that will be negative omega 1 EX. We're going to keep it positive, and we're going to say it's omega 1 UZ. Omega 1 UZ. And this direction cosine matrix shows what I was just saying, right? UZ is equal to negative EX. All right, so we have our terms written out. So we have negative omega 2 EZ, that was F and G, and then we have omega 1 UZ, that was D and F. I want these all to be in the same basis. It's going to make our lives easier. And since we're looking at the rate of change of this yellow vector, I'm going to write them all in terms of, the yellow basis. So EZ, what is EZ equal to in our yellow basis? Well, we already did that. EZ is equal to this column now, right? So it'll be cosine theta UR negative sine theta U theta, which I have written right here. So all I did was plug in for EZ. And then I distributed the negative omega 2, and this is our absolute angular velocity of frame D and frame G. Right. With that out of the way, now we can do a bunch of cross products. So dur dt is equal to omega dg crossed with ur, right? The absolute angular velocity of frame D crossed with the vector itself that we're interested in. This is just copied and pasted from above. That's just this. And then we're crossing it with ur. ur crossed with ur is 0. U theta crossed with ur is negative uz. So we pick up a negative uz. uz crossed with ur is u theta. And then we can just plug this right in. We can plug this dur dt right in for our velocity right here, and then boom, we have the velocity, right? All I did was plug that in, plug this in to here. So this is the velocity of point B. Next, let's find the acceleration. So the acceleration is equal to the derivative of the velocity vector. So I just took this, plugged it right in, and we're really doing the same thing again. It's just more bookkeeping. So remember, omega 1 is constant, r is constant, so the derivative of this right here is just r omega 1 du theta dt, and then we need to take the derivative of this term here. The negative r omega 2 I brought out to the outside, and then we have to do the product rule between the sine theta and uz. So the derivative of sine theta is theta dot cosine theta, theta dot cosine theta. So that's the first times the second plus the first sine theta times the derivative of the second, which is duz dt. All right, so now we got to find the rate of change of u theta and the rate of change of uz. Well, it's almost the same thing that we did before. Since we're still dealing with this frame D, it's the absolute angular velocity of frame D in G crossed with the vector itself, crossed with u theta. I probably should have written this out also, but I don't know why I didn't. this is equal to, this rate of change of uz, this is equal to omega d and g crossed with uz, right? So this and this, they're the same thing, except this one we're crossing with u theta, and this one we're crossing with uz. So we're just going to copy and paste again, right? The absolute angular velocity of d and g, we did that up here already. That's this term. So I'm just going to plop it right here. Boom. And we're crossing it with u theta. And then we do the cross product. ur crossed with u theta is uz. U theta crossed with u theta is 0. uz crossed with u theta is negative ur. And then we do the same thing. We take the absolute angular velocity right there, put it in here, but this time we're going to cross it with uz. So ur crossed with uz is negative u theta, so we lose this negative sign here, u theta. U theta crossed with uz is ur, so ur, and then uz crossed with uz is 0, right? So now we have the rate of change of u theta and the rate of change of uz. So now we just plug in for the acceleration, right? So what was our acceleration? It was r omega 1 times the rate of change of u theta, which we just found here. So we're going to plug this guy into here, minus r omega 2 times this plus sine theta, rate of change of uz, which we just found here. So we're going to take this and plug that in here. That is all I did right here. I just plugged in those rate of change terms that we just found. And then it's a bunch of algebra. I'm not going to walk through the algebra. Just recall that theta dot is omega 1. So going from here to here, I just replaced theta dot with omega 1. Again, this is just algebra, which you can look at and do on your own. But this is the acceleration of point B. And I'm going to leave it like this. The problem wanted us to write it back in the inertial frame. That's going to add way too much time to this video, and it's dumb. Why do that? It's already, this is already a perfectly legitimate answer. If you did want to do it, then you just have to replace ur, u theta, and uz with the red basis, which we found the relationship right here, right? So ur is equal to this in ex, ey, ez. U theta is equal to this, ex, ey, z, and uz is equal to this, ex, ey, z. So you could plug that in if you wanted to. It just makes a whole lot more terms that I feel like we don't really need to deal with. All right. There you go. We solved a problem from MIT. Wasn't too scary, right? That's all this is. All this dynamic stuff is just, what tools do you have in your toolbox, and keeping track of the algebra and not losing any terms along the way. That's the biggest mistake I make, is losing terms along the way. All right, that's it. I'll see you in the next video. Bye.